When Cooper first falls through the black hole, then he goes, oh, everything's black. No, like, you're not the only thing falling into a black hole. There's light from the entire rest of the universe that's falling in with you. I'm Dr. Paul Sutter. I'm a cosmologist, author, and NASA advisor. I also host my own YouTube channel and podcast. Today we'll be looking at the science of outer space in movies and TV and judging how real it is.
All in a line. A syzygy.
Did he say syzygy? Oh, good for him. I'd cry if I saw a syzygy. Syzygy is one of my favorite words in all of astronomy, and it's simply when more than two objects line up in a straight line. That's it. Anytime you have more than two objects in the same system, you have a three-body problem or four-body problem or on and on. And in this case, for this show, they have three suns that are all orbiting around each other in a very complicated way, and predicting how those stars are going to orbit is very challenging. A real three-body problem that we encounter all the time in the solar system is trying to predict the orbits of near-Earth asteroids. So if we see a little asteroid out there, and we're like, oh my gosh, is this gonna hit us or not? We have to calculate its trajectory through the solar system with all the gravitational influence of the sun, of the Earth, of Jupiter over there. And like that gets really, really complicated really quickly, which is why we're always revising and updating our predictions of orbital trajectories of asteroids.
The planet's under the gravitational force of all three suns!
Syzygies do create slightly stronger gravitational pulls, but this is a very extreme example that would not be realistic. When the moon and the sun are on the same side, we get extra tides. We get extra gravitational pull, but the oceans don't go flying out, buildings don't disintegrate and helicopters get pulled out into space. That's not a thing, because if the gravity was that strong, then everything on this planet would have been destroyed eons ago already.
When we unfold its higher dimensions, even a tiny proton becomes something very large indeed.
We have particle colliders all around the world that are accelerating protons and other particles to nearly the speed of light every single day. This is something we're good at. And the goal of this facility is to trigger nuclear fusion in that target. Unfolding a dimension is not a real thing. Yes, they say they can do that, but that's not how it works. The dimensions are the dimensions. It's just what space is. You can't take one of these compact dimensions and make it bigger. I would rate this a 3 out of 10 for realism. It started off okay with discussions of compact dimensions, but then lost some points because everything else after that was nonsense.
What I'm proposing is we start accelerating immediately.
His mannerisms of physicists and engineers explaining stuff to other people is dead on. We grab random stuff and just say, okay, imagine this is the particle, and then it's going over here, and it's exactly what we do.
We don't intercept with Earth at all, but we come close enough to get a gravity assist and adjust course.
The problem here that they were trying to face was that getting to Mars takes a really, really long time. It's really far away, and it's on its own orbit. And the idea here used in the movie, which is all mathematically sound, it's all solid orbital mechanics, was that if you are able to slingshot off the Earth, you get a speed boost and you can return back to Mars faster than you would have initially thought, as if you had launched it from the surface of the Earth.
You're Mars. Now, we're going too fast at this point to fall into orbit, but we can do a flyby.
Yes, when you're sending an object to another planet, you have a few choices. You can do a close flyby, or if you do it just right, it will come in and what we say is fall into orbit, where it'll end up making a permanent loop around that planet. And so if you're coming in too fast, you simply have too much energy. The gravity of the planet isn't strong enough to hold onto you. You're just going to be deflected in your path. They just had too much energy. They had too much speed. So there was a trade-off. They can get to Mars faster, but that means they can't stay there. He has to get to as high an altitude as possible so that he can intercept the oncoming spacecraft. But in order to do that, he has to get rid of mass. The less stuff he has, then for the same amount of fuel, the same amount of thrust, the higher up he can get. So that's true. This is Newton's third law in action. If I punch a hole and the gas escapes, the gas goes this way, I go this way. But if it's on the palm of my hand, it's away from my center, which means it won't just push me, it will twist me. And so if you actually tried that, you would end up tumbling uncontrollably. This is gonna sound crude, but if he had punctured his crotch, that would be on a line to his center of mass, and that would have propelled him straight up.
I got it!
In space, everything is complicated. You can't move around as nimbly as you can without a spacesuit, and you're trying to operate in 3 dimensions, so it's not like a relay race where you're guaranteed to have the ground underneath you the whole time. And so you're trying to match this precise speed in this alien environment in 3 dimensions, not something our monkey brains are really capable of handling, and it's just all hard, and it makes for a great movie. I would rate these clips a 10. Full 10, 100%. I love this, but it's just such a wonderful movie, and it's all about science and science saving the day. So much good science in the black hole image. Light follows the curves, the hills and valleys of space-time. And these curves are set by massive objects. This was one of the earliest tests of Einstein's theory of relativity. And black holes bend space a lot. And so what we're seeing is there's a thin disk called an accretion disk surrounding the black hole. But if you're standing on one side of the black hole, light from the back end, which normally you wouldn't see because, black hole in the way, there's light that's going up this way, but then gets bent and curves right to you.
Goodbye, Tars.
Goodbye, Dr. Brent.
Newton's third law is for every action, there is an equal and opposite reaction. And this is the fundamental basis for space travel. We push against the air to get our airplanes to go, but in space, there's no ground. There's no air. So we can only push against ourselves. If we throw something away from us, that propels us in the equal and opposite direction. And so what I think he's going for here, old Cooper, to get him away from that orbit, if he pushes something towards the black hole, that will nudge the spacecraft away from that orbit and give it a safe escape.
Approaching the event horizon. Port side, dipping down beneath it.
The event horizon is the one-way barrier. This is the edge of the black hole. This is the point of no return, that if you cross the event horizon, then gravity is so strong, it's so overwhelming that nothing, not even light, can escape.
It's all black. Tars, do you read me?
When Cooper first falls through the black hole, then he goes, oh, everything's black. No, you're not the only thing falling into a black hole. There's light from the entire rest of the universe that's falling in with you. For a supermassive black hole like this, like Gargantua in the movie, you've got a handful of seconds from the moment you cross the event horizon to the time you hit the singularity. That was an incredibly accurate depiction. In fact, it's one of the most accurate depictions of the environment around a black hole ever made. I would give it a 9. Okay, a point off because, it's not actually dark in there, but honestly, we don't know what actually happens inside of a black hole, so that's fair game.
So how do we make it? Awaken the heart of a dying star.
Thor needs the energy from a dying star to create his new weapon, which is called Stormbreaker. Stars die when they run out of fuel. So every star in the universe is fuses elements into heavier ones, which releases some energy. But no matter what star you have, iron is always the end of the limit. That's the most you can get, because after that, the fusion process doesn't release energy, it takes it. So once a star fuses iron, it's done. There's a lot of good Newtonian mechanics there with the spinning of the rocket and then letting it go and then grabbing it and using that's its own propulsion to move this massive ring thing. A Dyson sphere is this concept developed by famed physicist and mathematician Freeman Dyson, where the idea is like, hey, if you're a civilization on the move, you got your wind power, your nuclear power, you got your solar power. Eventually, you're going to tap out all of the energy sources available on a planet. So, hey, if you need a lot of energy, what if you pulverize your planet and turn it into a whole bunch of solar panels facing inwards on your star? And that way you can capture as much light as possible. Most of the light emitted by the sun just goes off into empty space, misses us completely. So if you capture that, then you can use it and make a new hammer. Once a star is dead, it's just dead. Just let it go, man. But neutron stars can release enormous amounts of energy. And that's because you have an object that's one step away from a black hole. You've got this incredibly dense ball of material. Fastest rotating neutron stars rotate at over 10,000 RPM. That's faster than a kitchen blender. There are enormous energies involved with this compression of matter rotating at that speed. And so, yeah, they can power up some seriously incredible energetic outbursts. Yeah, that's what struck out to me the most, actually, is like they awaken this dying star, whatever that is, and it sends this like energy beam out, and then the characters are like, oh, that's cool. Like, these are energies that can rip apart planets, that can vaporize anything. To be close to a source of energy like that, you wouldn't get to look at it. You would just be destroyed. We're gonna have to scrape the bottom of the barrel here for accuracy. I would rate this clip a 4. Neutron stars are a real thing. Neutron stars actually have a lot of energy, and Newton's law is still valid in the comic book universe.
6, 5, 4.
When this device switched on and we had the battleship out front, full of all the observers, and the battleship started tilting towards it, and I was thinking, like, if this thing has immense gravitational pull, why is there just a tilt instead of the whole ship being pulled along with all the water? I mean, it looked amazing. It was very cool to look at. So this machine consists of a passenger pod, a little vessel, surrounded by some protective shielding and metal, and then a series of rings. Through various alien magic, the rings open up a wormhole and then drop that passenger sphere in, and then the passenger sphere travels through the wormhole to the distant destination. A wormhole is a hypothetical tunnel or bridge through space and time that can connect two very, very distant regions in space and time and bring them closer together so that you don't have to go the long way, which might involve a whole lot of light years. There's nothing scientific about using spinning rings to create a wormhole, but they sure do look cool. The only way we know to create a wormhole is to start off with a blob of what's called exotic matter. What makes it exotic is that it has negative mass. If you've got some exotic matter that weighs negative mass, then you can potentially reconfigure space-time in just the right way to create a stable wormhole. And we don't think it exists because it would kind of violate everything we know about like momentum and energy and all of our experience in physics. Like if you had a ball that weighed -5 pounds and you kicked it, it would go flying in the opposite direction. And if you dropped it, it would go flying upwards. And that seems kind of wrong.
I'm in another wormhole now!
It's a triple, no, quadruple system.
One thing that struck me, though, actually, that seemed very accurate was her attempt to narrate what she was seeing as she was going. And what that reminded me of is if you listen to the Apollo 11 tapes, and the astronauts were trained to narrate what they were seeing. Our view from the Earth was just little cameras, little staticky images. The astronauts themselves could see in so much more detail. And so they were trained, like, don't just look, but keep describing what you see.
Although the surface appears to be very, very fine-grained as you get close to it.
We don't know what a wormhole looks like. We've never traveled down one. We don't even think they exist. You can visualize it however you want. I would rate this clip a 7. Jodie Foster maintained her composure while traveling through a wormhole. I'm pretty sure I'd be barfing and freaking out the whole time. So good for her. When they're approaching the moon to do that lunar roll, as they called it, they turned their spacecraft towards the moon as if they were fighter jets banking into a turn. But this is space. There's no air. There's nothing to bank against. You can just go with it. You're fine. You're gonna go around the moon. It's all good.
9.5 G's for 11 minutes. I'd start praying about it right now.
So 9.5 Gs means that the pressure you'll feel, the weight you'll get pushed up against your chair, is 9.5 times stronger than our normal experience of gravity. This is generally going to be miserable. 9.5 strikes me as a very unrealistic number, especially for that length of time. They're just going to pass out and be starved of oxygen for 10 minutes, which is dead. The astronauts are getting a gravity assist from the moon so that they can get a speed boost to land on an asteroid. The idea is you need to catch up to it. You need to match speeds with it. Otherwise, you're just going to crash into it. So launching from the surface of the Earth, we can do this. We've done rendezvous missions with moving asteroids and comets. There's no reason for them to experience G-forces during a slingshot maneuver. The whole time you're doing a slingshot maneuver, you're in space. There's hardly any gravity. You don't feel any gravity when you're in space. And when you're doing this slingshot maneuver around the moon or any object, the moon is big. Yes, you're accelerating, but that boost is taking place over the course of hours as you orbit around the moon. So it's a very slow and gentle process. So you don't feel anything extra. And I saw them in that clip. They're like burning their rockets. And I was like, man, that takes a lot of fuel. And I was like, if you have enough fuel to be already in space and then do this accelerated boost maneuver, then just skip the moon and you can just go right to the asteroid. But that's why they don't put me in charge of writing movies. I would rate this clip a 3.
We're being pulled off course.
How?
I'm not certain. It appears to be some kind of graviton surge.
Graviton is a real word. If you were approaching a void, it'd actually be the opposite of a surge because there's less stuff. There's less matter in a void. There's less gravity in a void.
What happened to the stars?
I happen to be one of the top 5 experts on cosmic voids in the world, and that's because there are about 5 people working on voids in the whole world. And they're simply places where there ain't much going on. They have almost no matter within them. If you were to transport our solar system into the middle of a void, not only would there be no stars on the sky, because there'd be no stars around us, you could take almost any telescope and you wouldn't see a single thing, because all the nearest galaxies would be so far away from you that you would need an incredibly advanced instrument to detect them.
But they only pull matter in one direction, into the void. We've calculated the outer circumference at approximately 9 light years.
Oh, circumference is 9 light years. That means the radius is even smaller. This is a tiny thing. This is nothing. Voids are huge. They are amongst the largest things in the universe. The smallest voids are like 20 million light years across on a side. Voids aren't in galaxies. Galaxies are on the edge of voids. They're huge. And if you were to end up in a void, you're not coming out anytime soon.
50,000 kilometers to normal space.
So the easiest way to leave a void is to point yourself to the nearest galaxy and you pack a sandwich and bring a book, because it's gonna take you a while. There are no shortcuts, there are no cheat codes, you just gotta take the slow way. I would rate this clip a 2. The only accurate part of this clip is that the word void is a real science term in astrophysics and cosmology. That's it. What really struck me, which was so beautiful and very, very accurate, was the actual surface of the sun. You know, as the spacecraft is plunging into the sun, we get these great images of these giant arcs and flares and prominences, and the sun really does look like that. We have high-resolution imagery of the surface of the sun that shows just how dynamic and volatile and active and gorgeous it is. In real life, you wouldn't even get as close as that spacecraft got to the sun. With our current technologies, within a few million miles, you get cooked.
You could observe 3.1% for a period of not longer than 30 seconds.
The amount of solar energy that we receive on the Earth is 0.000000045% of the total solar output. The character is told that he can safely observe the sun for a limited amount of time at 3.1% of its total brightness. I wouldn't necessarily trust the computer. Maybe the math all works out, but I'm not playing games. I would give it a 6 because the images of the sun were gorgeous, accurate, spot on, and most people don't get to realize just how gorgeous and dynamic the sun is.
The law of relativity prohibits faster than light travel.
Relativity, yes, we can't break the law of relativity. We can go around it.
I've seen this movie like maybe a million times. We know in our universe that causes always precede effects, and the fastest that a cause can lead to an effect is the speed of light. Going faster than light allows you to have effects that come before their own causes. It breaks down the entire causal structure of the universe, which is why we're pretty sure you can't do it.
Ship doesn't really go faster than light. What it does is it creates a dimensional gateway. It folds space so that point A and point B coexist in the same space and time.
It's a little fuzzy because we don't know how wormholes actually work, but we do know mathematically that they do act like tunnels where you can have as short as a distance as you want between any 2 points. Now, whether this means the actual space-time is getting folded up in a higher dimensional way, that's more of an analogy and a metaphor than what actually happens, which is kind of impossible to describe in words, but that's why we have mathematics, so that we can do stuff that words can't let us do. That is the core of the Event Horizon's gravity drive. They use this to, in the movie, fold space and time so that your starting point and ending point are the exact same place. My best guess as to why this guy's getting sucked into the gravity drive is that when this thing is turning on and generating a singularity, you're taking a whole bunch of matter and compressing it down into a very tiny volume, which generates enormous gravitational forces. That should have ripped the ship apart. You get these enormous things called tidal forces that can stretch and deform matter around it. And so it's like, if it's strong enough to act on a person, it's strong enough to act on everything surrounding the person. No, this was very inaccurate because it made it look like the black hole was two-dimensional. The surface of a black hole is three-dimensional. They're spheres. They're not funnels like this. They're spheres, almost like a planet sitting there that you could orbit around from any direction. I'm going to give a 4. It gets a 4 because that's not really how wormholes work, so lots of points off. But Sam Neill nailing the attitudes of a tired professor, all for it. My favorite space movie / TV show is actually The Expanse. It's a wonderful story, complex, intricate story, and yeah, there are some non-realistic magical elements, but they work really hard to not just set up the physics correctly, but what society would look like in space, and I really appreciate that. If you like this video, why not click on the next one?